Have you ever wondered how your smartphone fits so much power in your pocket, or how your car knows when to brake automatically? The answer lies in tiny, mighty devices called semiconductors. Semiconductors are materials that conduct electricity, but not as well as conductors like copper. This unique property allows them to control the flow of electricity very precisely. Think of them as tiny gatekeepers, directing the flow of electrons to make our electronics work. These unassuming materials are the heart of modern electronics. Without semiconductors, we wouldn't have smartphones, computers, or even modern cars. They are essential for everything from communication and entertainment to healthcare and transportation. Semiconductors have revolutionized our world, and their importance continues to grow as technology advances. Let's dive deeper into the world of these tiny wonders and explore how they're made and used. The journey of a semiconductor starts with something surprisingly simple: sand. Sand contains silica, the primary source of silicon, the most common semiconductor material. The first step is extracting pure silicon from silica. This involves heating silica at high temperatures to isolate the silicon. The purified silicon is then melted and grown into large cylindrical crystals called ingots. These ingots are then sliced into thin, round wafers, which form the base for building semiconductors. The wafers undergo a series of complex processes, including polishing, layering, and etching, to create the intricate circuits and components that give semiconductors their functionality. The manufacturing process is incredibly precise, requiring specialized equipment and cleanroom environments to prevent even the tiniest dust particles from interfering with the delicate structures. It's a testament to human ingenuity and the incredible power of these tiny devices. Creating a functional semiconductor involves a process called doping. Doping involves adding tiny amounts of impurities to the silicon, altering its electrical properties. Adding impurities like phosphorus creates an N-type semiconductor, with extra electrons that can easily flow. Adding boron creates a P-type semiconductor with holes that act like positive charges, attracting electrons. The real magic happens when we combine N-type and P-type semiconductors. This creates a PN junction, the fundamental building block of most electronic devices. PN junctions act like tiny switches, allowing current to flow in one direction but blocking it in the other. By controlling the doping and arrangement of PN junctions, engineers can create transistors, diodes, and integrated circuits, the brains behind our electronic devices. Semiconductors in action, powering innovation across industries. The applications of semiconductors are vast and ever-expanding. They are the backbone of countless industries, driving innovation and shaping our modern world. Consumer electronics like smartphones and laptops rely on semiconductors. In cars, semiconductors control engine performance and safety features. Solar panels and wind turbines use semiconductors to manage energy. In healthcare, semiconductors are crucial for medical devices. Telecommunications rely on semiconductors for data transmission. Industrial automation uses semiconductors for precise control. Computing, from supercomputers to data centers, depends on semiconductors. Aerospace relies on semiconductors for navigation and control. AI and big data analytics depend on advanced semiconductors. Section 5. The Semiconductor Giants, leading the charge in a global industry. The semiconductor industry is a global powerhouse, with companies and countries competing for dominance in this critical sector. The United States, Taiwan, South Korea, and Japan are major players in semiconductor design and manufacturing. Companies like Intel, Samsung, TSMC, and SK Hynix are industry leaders, constantly pushing the boundaries of semiconductor technology. The production of semiconductors is a complex and capital-intensive process, requiring significant investment in research, development, and manufacturing facilities. The competition is fierce, driven by the constant demand for smaller, faster, and more powerful chips. Section 6. The future is semiconducting, innovations and challenges ahead. The future of semiconductors is brimming with possibilities. Researchers are constantly working on new materials and designs. Quantum computing relies heavily on advanced semiconductors. Quantum computers can solve complex problems beyond classical computers. Neuromorphic computing mimics the human brain's structure and function. Neuromorphic chips could revolutionize AI and machine learning. The The semiconductor industry faces increasing complexity and costs. Global demand often outstrips supply, causing shortages. Despite challenges, semiconductors will shape our future.